Welcome to the Tailings podcast, where key papers on tailings management and geotechnical engineering take center stage. Founded by Mohammed Sabi, this podcast is guided by a vision to share knowledge and inspire innovation. While Mohammed works behind the scenes, his commitment drives every insightful conversation, exploring the challenges and advancements shaping the industry. Today, we're taking a deep dive into a field that's literally the foundation of safe construction critical state soil mechanics, or CSSM, as the cool kids call it. It's a journey over 125 years in the making, from early dam disasters to cutting-edge research that's helping us prevent future tragedies. And, it all starts with a pretty sobering realization. Soil isn't just dirt.
That's right. It's a complex material with its own set of behaviors, and understanding those behaviors is crucial, especially when we're talking about tailings dams.
Exactly. We've all seen the headlines about those catastrophic dam failures. And they often come down to not fully grasping how soil reacts under pressure. It's like thinking you can build a house on a foundation of jelly. Recipe for disaster, right?
Absolutely. And early engineers learned that the hard way. Back in 1918, the Calaveras Dam failure was a stark reminder that we can't just treat soil like a simple inert material. It was a wake-up call that led to a whole new way of thinking about soil, as a collection of particles with varying void ratios.
Void ratios. Now, I remember that term from school. And let's be honest, it wasn't exactly the most thrilling topic.
Yeah.
But you're telling me it's key to understanding why some structures stand strong while others crumble.
Think of it like this. Imagine soil particles as puzzle pieces. If they fit tightly together, you get a strong interlocking structure. But if they're loosely scattered, the whole thing becomes unstable. That's essentially what void ratio is all about. How tightly packed those particles are.
Okay, that's a much better image than what I had in my head. So how did engineers start figuring out this whole void ratio thing? Did they have fancy lab equipment back then?
Not quite. But even back in 1885, Osborne Reynolds had this groundbreaking idea that a soil's packing density, its void ratio, directly affects how much it changes volume under stress. And this was long before we had all the high-tech gadgets we use today.
Wow. Talk about ahead of his time. So they were already starting to connect the dots between packing density and the stability of a structure.
Yeah.
But how did they actually apply that knowledge to building safer dams?
Well, it took more research, and sadly, some more dam failures to really drive the point home. In the 1930s, Arthur Casagran and the Corps of Engineers were working on the Franklin Falls Dam. They were determined to avoid another disaster, especially those caused by soil liquefaction.
Liquefaction, that's when the soil basically turns to quicksand, right? Not exactly what you want holding up a massive dam.
Exactly. Casagran focused on this concept of the critical void ratio. Imagine it as a tipping point for soil behavior. If the soil's denser than this critical void ratio, it tends to dilate under pressure, meaning the particles push each other apart. This actually makes the soil stronger.
So it's like those expanding toys that get bigger when you squeeze them. Counterintuitive, but I kind of like it.
It is a bit like that. But if the void ratio is higher than that critical point, the opposite happens. The soil contracts or gets even more tightly packed when you put pressure on it. This is where liquefaction becomes a real threat, because the water trapped in the soil can't escape, and the whole structure loses its strength.
Okay, so finding that critical void ratio is like finding the magic number for building on soil. But how did engineers figure out how to use that number in the real world, where you've got tons of soil and a massive dam on top of it?
Well, they realized that just knowing the critical void ratio wasn't enough. They needed to see how it related to the actual stresses the soil would experience in a dam. That's when the critical state locus, or CSL, came into play.
Ah, yes, the CSL. Those soil mechanics diagrams with the CSL always looked a bit intimidating to me, like some secret code only engineers could crack. Can you break it down for us, mere mortals?
It's not as complicated as it sounds. Basically, the CSL is a line on a graph that shows the relationship between a soil's void ratio and how much pressure it can handle before reaching what we call the critical state.
So the critical state is that tipping point again, where the soil is on the verge of collapse.
Right. But here's what's fascinating. At the critical state, the soil can deform without changing its volume or strength. It's like it's found this delicate balance where it can keep changing shape without falling apart. And that tells us a lot about how it'll behave under the weight of a dam.
So by understanding the CSL, engineers could start predicting whether a soil would compact and get stronger or liquefy and potentially cause a catastrophic dam failure. That seems like a huge breakthrough.
It was. And it opened the door to even more research into what makes soil strong. In 1948, Donald Taylor proposed this idea that we should think about soil strength in terms of two components: friction and dilation.
Friction makes sense, like rubbing your hands together. It takes force to overcome that resistance. But
Mhm.
dilation, remind me how that fits into soil strength.
Remember how dense soils dilate, those particles pushing each other apart when you apply pressure? Well, that dilation actually takes energy, and that contributes to the overall strength of the soil. So dense soils are stronger because they push back, requiring more energy to fail.
Okay, so it's like trying to compress a spring. The more you compress it, the harder it pushes back. I'm starting to see how these pieces fit together.
And the research kept building on these foundational ideas. Bishop in 1950 and Rowe in 1962 really emphasized that soil strength isn't just about the soil itself, it's also about how it changes under pressure. The way those particles rearrange and interact is crucial.
So it's not enough to just test a soil sample in the lab. You have to consider how it'll evolve under stress, which I imagine is a lot harder to figure out. It sounds like engineers were really digging into the nitty-gritty of soil behavior by this point. Did all this research lead to any...
Absolutely. In the 1960s, this revolutionary mathematical model called CAM-CLAY emerged. It was a bold attempt to predict soil behavior using all these principles of CSSM.
Cam Clay, I've heard that name before. But didn't it have some limitations?
It did. As groundbreaking as it was, CAM-CLAY sometimes struggled, especially when it came to those really dense soils.
Hold on, so a model that's supposed to predict soil strength fails when the soil is stronger. That seems a bit ironic, doesn't it?
It does, and this became a real issue for engineers working on projects like Arctic oil platforms, which needed to withstand incredible forces. They were using these dense, hydraulically placed sand fills, and Cam Clay often predicted strengths far higher than what they were observing in reality.
Okay, so Cam Clay, while a step in the right direction, wasn't the final answer. It's like having a map that only shows half the terrain. What happened next? Did researchers abandon CSSM altogether?
Not at all. Instead, they doubled down, searching for that missing piece of the puzzle that would explain those discrepancies. And that search led to one of the most important advancements in CSSM, the state parameter.
The state parameter. Here's where things get really interesting. Tell us more about this game changer.
The state parameter, represented by the Greek letter psi AC, basically tells you how far a soil's current state is from that critical state we talked about earlier. It's a relatively simple concept, but it had a huge impact because it allowed engineers to make more accurate predictions across a wider range of soil densities and stresses.
So it's like a fine-tuning knob that adjusts the model to the actual density of the soil, making the predictions more realistic.
Exactly. And this revolutionized our understanding of soil strength. In 1985, Ken Ben and Mike Jeffries showed that the state parameter could accurately predict the strength of different sands. They basically cracked the code for a whole range of soil behaviors.
Okay, this state parameter sounded like the hero of our CSSM story. But we're still dealing with theoretical models here. How did these advancements translate into something engineers could actually use on a real-world dam project? How do you measure something as abstract as the state parameter when you're dealing with tons of soil?
That's where a tool called the cone penetration test, or CPT, comes into play. It's basically a probe that you push into the ground, and the resistance it encounters tells you a lot about the soil's properties. And crucially, we can connect those CPT measurements to the state parameter, giving us a way to assess the soil's vulnerability to liquefaction right there in the field.
So the CPT is like a window into the soul of the soil, revealing its secrets and whether it's got what it takes to hold up a dam.
That's a great way to put it. But just like any language, the CPT data needs to be interpreted correctly. And that brings us to another key innovation: calibration chambers. These are basically giant test setups where we can measure how the CPT responds to different soil conditions.
So you're testing the test itself to make sure it's giving you accurate readings for the specific type of soil you're dealing with. Seems like a lot of work to calibrate a tool, but I guess accuracy is everything when you're talking about the stability of a dam.
You're absolutely right. Calibration chambers help us establish a precise link between the CPT measurements and the state parameter for a particular soil. It's all about fine-tuning our understanding to get the clearest picture of that soil's liquefaction potential.
This is all incredibly fascinating. It's like we've gone from treating soil like a simple material to realizing it's this complex, dynamic system with its own language and set of rules. But I know our listeners are eager to hear how all of this connects back to those catastrophic dam failures. We've laid the groundwork for understanding soil behavior, but how do we actually use that knowledge to prevent future disasters?
That's a great question, and it leads us to the heart of the matter, static liquefaction. You see, most people associate liquefaction with earthquakes, but it can happen even in seemingly stable, drained soils. And that's where things get really dangerous.
Wait, so even if a dam looks solid and the monitoring systems aren't showing any red flags, it could still be at risk of suddenly collapsing. That's terrifying.
It is. And the tragic Fundão dam failure in Brazil is a prime example of this. The investigation pointed to static liquefaction as the likely culprit. It was a devastating reminder that relying solely on traditional monitoring might not be enough. We need a deeper understanding of soil behavior, one that takes into account this potential for hidden danger.
So what can we do to prevent these static liquefaction disasters? Is it all about building stronger dams, or are there other strategies?
There are several strategies, and they all stem from the principles of CSSM. We can maintain unsaturated conditions in the soil, ensure adequate compaction, and design structures that keep stresses below critical thresholds.
Okay, let's break down these strategies one by one. What's the thinking behind maintaining unsaturated conditions?
It all comes back to pore water pressure. If the soil is unsaturated, meaning there's air in the pores along with water, then any changes in the soil volume will compress the air rather than the water. This reduces the risk of a sudden pressure buildup that can lead to liquefaction.
So it's like having built-in shock absorbers in the soil.
Yeah.
Smart.
Exactly. But of course, there are challenges. It's most effective in drier climates, and you need to be absolutely sure the entire soil mass stays unsaturated, which can be tricky, especially deeper down where stresses are higher.
That makes sense. So what about compaction? How does packing the soil tighter help prevent liquefaction?
Remember that critical void ratio we talked about earlier? Well, compaction is all about getting that void ratio down, making the soil denser and pushing it into that safer dilutant zone.
So it's like squeezing those soil particles together so they're less likely to shift and collapse under pressure.
Exactly. And here's where the state parameter comes in handy again. It gives us a quantitative measure of how far we need to compact the soil to push it away from that critical point.
Okay, so we've got unsaturated conditions and compaction. What about that third strategy? Designing structures to keep stresses below critical thresholds. What does that entail?
This is all about understanding the limits of the soil and making sure the dam never pushes those limits. It means considering the height of the dam, the steepness of its slopes, and even the rate at which we add tailings. We need to carefully analyze where stresses might concentrate, those areas that could become weak points.
So it's like a delicate balancing act between the weight and volume of the tailings, the design of the dam, and the strength of that foundation soil.
Precisely. And CSSM gives us the tools to analyze and predict how the soil will behave under all those varying conditions. By incorporating the state parameter, we can determine the safe operating limits and make sure we never push the soil into a state where it's prone to liquefaction.
This is all incredibly insightful. But I'm wondering, what if, despite our best efforts, liquefaction does occur? Is it game over for the dam?
That's a great question. And it leads us to another important aspect of CSM, understanding post-liquefaction strength.
Wait, so even after the soil liquefies, there's still some strength left. That seems counterintuitive.
It might seem surprising, but yes, even liquefied soil retains some strength. And that strength can be a crucial factor in whether a dam survives. But there's a catch. That post-liquefaction strength is often much lower than what we might expect based on lab tests.
So even in a worst-case scenario, there's a chance the dam might hold if we've accounted for that residual strength. It's like having a backup plan for a backup plan.
Exactly. But accurately predicting that post-liquefaction strength is a complex challenge. And that's what we'll dive into in the next part of our deep dive.
This has been an incredible journey so far, and I'm already on the edge of my seat to hear what comes next. We've gone from simple puzzle pieces to complex mathematical models, and it's all about understanding the hidden language of soil and using it to build a safer future. Stay tuned for part 2, where we'll uncover the secrets of post-liquefaction strength and explore the tools that help us predict it.
Welcome back to our deep dive into critical state soil mechanics. I'm excited to continue our exploration of this vital field, especially now that we've laid the groundwork for understanding how soil behaves under pressure.
Me too. Last time we left our listeners with a bit of a cliffhanger, this idea that even after soil liquefies, it still has some strength left. But you mentioned it's tricky to predict that post-liquefaction strength accurately. Why is that?
You see, while lab tests can give us some clues, the real world is a much messier place. Soil properties vary, stresses change over time, and drainage patterns can be unpredictable. One of the key factors that affects post-liquefaction strength is something we call the stress path.
Stress path. That sounds a bit like a GPS route for soil particles.
It's a great analogy. Imagine a tiny piece of soil deep inside a tailings dam. As more tailings are added above it, the stresses on that soil element increase. And the way those stresses change over time, that's the stress path. And different paths can lead to different post-liquefaction strength.
So it's not just about how much stress the soil experiences, but also how that stress changes over time. That seems like a lot of variables to keep track of. Is it even possible to predict how soil will behave after liquefaction with all those factors at play?
It's definitely complex, but thankfully, CSSM provides the tools to analyze those stress paths and make reasonable estimates. One key insight is that post-liquefaction strength isn't just a fixed property of the soil, it's also influenced by the initial state of the soil, which we can capture using that handy state parameter we talked about earlier.
So a denser soil with a lower state parameter would generally have a higher post-liquefaction strength than a looser soil.
That's a good rule of thumb. But there's another important factor: the soil's compressibility. Think about it. When soil liquefies, it tends to contract. And if that contraction is restricted by the surrounding soil or the dam structure, it can actually increase the post-liquefaction strength.
Hold on, so squeezing a liquefied soil makes it stronger. That seems counterintuitive.
It does seem odd, but think about it like squeezing a wet sponge in a container. The more you confine it, the harder it gets to squeeze any more water out. In a way, that confinement increases the sponge's resistance.
Okay, that makes sense. So we've got the state parameter and compressibility, both influencing post-liquefaction strength. But how do we actually measure and predict these things in a real-world dam? Are we talking about complicated calculations in supercomputers?
Well, we do have sophisticated computer models that help us simulate these complex processes. They're based on those fundamental CSSM principles we discussed, like the critical state locus, stress dilatancy, and of course the state parameter. These models allow us to consider those intricate stress paths and how soil particles interact with pore water.
So they're like virtual laboratories where we can test different scenarios and see how the soil responds.
Exactly. And while some of these models can be quite computationally demanding, there are also simplified versions that are accessible to practicing engineers. They can run these models on their computers to get a better grasp of post-liquefaction behavior.
That's great news. It's like putting powerful analytical tools right in the hands of the people who need them most. But even with these models, I imagine predicting post-liquefaction strength is still a bit like trying to predict the weather. There are just so many variables. Are there other ways we can improve our understanding of this phenomenon?
You're right. Models alone aren't enough. We also need to learn from the past, and that's where case histories come in.
Case histories. You mean studying past failures to understand what went wrong?
Exactly. By carefully examining well-documented cases of liquefaction, we can glean valuable insights into the factors that contribute to failures and, importantly, the post-liquefaction behavior of different soils.
So it's like forensic science for soils, digging into the evidence to uncover the secrets of liquefaction.
That's a great way to put it. And one of the pioneers in this field is Mike Jeffries, who we mentioned earlier in connection with the state parameter. He's done extensive work compiling and analyzing case histories, and his research has been instrumental in advancing our understanding of post-liquefaction strength.
That's fascinating. So by combining these sophisticated models with the lessons learned from real-world failures, we're getting a much clearer picture of what happens to soil after liquefaction. But how do we translate all this knowledge into practical design guidelines for tailings dams?
That's where engineering judgment and experience really come into play. There's no one-size-fits-all answer, but CSSM provides a framework for making more informed decisions. In some cases, it might be appropriate to design the dam to withstand initial liquefaction and rely on that post-liquefaction strength to maintain stability. This might involve building a wider base or using reinforcement techniques to bolster the overall strength. In other cases, it might be essential to avoid liquefaction altogether using techniques like compaction, drainage, or other methods to keep the soil in a safe zone.
So it's not just about building a stronger dam, it's about understanding the specific risks and tailoring the design to the unique conditions of the site and the tailings material.
Exactly, and I think it's important to emphasize that CSSM isn't just about complex models and equations. It's about fostering a deeper understanding of soil behavior and using that knowledge to make better decisions. It's about challenging our assumptions and embracing new tools and methods that can help us design safer and more sustainable structures.
That's a powerful message. But I have another question. We've been talking a lot about sands, but what about silts? They're a major part of many tailings deposits, And we know they can also be susceptible to liquefaction. Does CSSM apply to silts as well?
That's a great question. And it highlights an area that needs more research. Silts are often called the problem child of soil mechanics. They don't behave quite like sands or clays, and they can be difficult to test and characterize in the lab.
Why is that? What makes silts so challenging?
Well, silts are essentially a mixture of sand and clay-sized particles, and their behavior can be quite unpredictable depending on the proportions of those components. They're also very sensitive to disturbance. Simply handling or sampling them improperly can change their properties significantly, and their particle size makes them prone to problems like piping and erosion, which can really threaten a dam's stability.
So they're a bit like the Goldilocks of soils. Not too coarse, not too fine, but just difficult enough to create headaches for engineers.
That's a perfect analogy, but here's the good news. CSSM principles still apply. Remember, CSSM is based on the idea that soil is a particulate material, and those fundamental relationships we've been discussing, like the critical state locus and stress dilatancy, hold true for silts as well. The challenge lies in accurately determining their properties, particularly those related to strength and dilation.
So it's like we need to adjust our instruments and refine our understanding to unlock the secrets of those tricky silts.
Precisely. And that's where ongoing research is vital. We need to develop more robust testing methods and fine-tune our models to accurately predict silt behavior, especially under the high stresses and complex conditions we find in tailings dams. Because as we've seen, the consequences of getting it wrong can be catastrophic.
That's a sobering thought. But I'm also sensing a note of optimism in your voice. It sounds like there's a lot of exciting research happening in this field, and we're making real progress in understanding these elusive silts.
You're absolutely right. The challenges are significant, but so are the opportunities. With advancements in testing technology, modeling techniques, and our fundamental understanding of soil behavior, we're better equipped than ever to design safer and more sustainable tailings dams, even in those challenging silt-rich environments.
This has been an incredible journey so far. We've explored the complexities of post-liquefaction strength and even delved into the world of those tricky silts. But there's one crucial question we haven't answered yet. How do we translate all of this knowledge into action? How do engineers actually apply these concepts to real-world tailings dams? Join us for part 3, where we'll explore the tools and techniques that bridge the gap between theory and practice. We'll delve into the fascinating world of CBT interpretation, calibration chambers, and the art of making informed engineering decisions. Welcome back to the final part of our deep dive into critical state soil mechanics. We've covered a lot of ground from the theoretical foundations to the challenges of predicting post-liquefaction strength. Now it's time to bring it all together and see how engineers actually use this knowledge to design and manage safe tailings dams in the real world.
That's right. It's time to bridge the gap between theory and practice. And one of the key tools that helps us do that is the cone penetration test, or CPT. We've mentioned it throughout this deep dive, but now let's really explore its power in assessing liquefaction potential.
Perfect. Our listeners have heard us mention CPT a lot, so I think they're ready to hear how this seemingly simple test can provide such valuable insights into what's going on beneath the surface.
It really is a remarkable tool. Remember, the CPT involves pushing that cone-shaped probe into the ground and measuring the resistance it encounters. That resistance gives us clues about the soil's strength, density, and even its stress history. And the best part, we can directly link those measurements to the state parameter, which, as we've discussed, is a key indicator of a soil's susceptibility to liquefaction.
So like a fingerprint for the soil, revealing its unique characteristics and potential for trouble.
Exactly. But just like fingerprints, CPT data needs to be carefully analyzed to extract meaningful information. There are different approaches, some more complex than others, but the goal is always the same: to determine that all-important state parameter and assess the soil's vulnerability to liquefaction.
Can you walk us through some of those approaches? What are the key steps involved in interpreting CPT data?
One common approach is called the screening method. It uses empirical correlations. Basically, relationships we've observed between CPT measurements and different types of soil behavior to estimate the state parameter. It's a relatively quick and easy way to get a general sense of the soil conditions and identify areas that might warrant further investigation.
So it's like a first pass, a way to quickly scan the site and see if any areas are waving red flags.
That's a great way to put it. It's a valuable starting point. But for critical structures like tailings dams, we often need a more refined and site-specific assessment. And that's where those calibration chambers we mentioned earlier come in.
Ah, yes, those giant test setups where you can measure the CPT's response under controlled conditions. It sounds like a pretty elaborate way to calibrate a tool, but I'm guessing it's worth the effort when it comes to dam safety.
Absolutely. Calibration chambers are essential for establishing a robust relationship between CPT measurements and the state parameter for a specific soil. You see, the CPT's response can be influenced by several factors: the type of soil, how much stress it's under, even the presence of groundwater.
So you're basically fine-tuning the CPT to the specific soil conditions at the site, like adjusting a recipe based on the ingredients and oven temperature.
That's a great analogy. By testing the soil in a calibration chamber, we can determine how the CPT responds to different densities, stress levels, and drainage conditions. This allows us to develop site-specific correlations that give us a much more accurate estimate of the state parameter.
It all comes down to getting the most accurate picture possible of the soil's liquefaction potential. But once we have that information, how do engineers actually use it to make decisions about the design and management of a tailings dam?
Well, that's where the real skill comes in, translating all this data and knowledge into practical actions. Once we have a reliable estimate of the state parameter, we can use it to assess the liquefaction potential of different zones within the dam. We can identify areas that are most at risk and develop strategies to mitigate those risks.
So it's like having a risk map for the dam, highlighting the areas that need extra attention.
Exactly. And those mitigation strategies can involve a variety of approaches: compacting the soil to increase its density and lower the state parameter, installing drainage systems to manage poor water pressure, modifying the dam's geometry to reduce stress concentrations, or even using reinforcement techniques to boost the overall strength.
It sounds like a multi-pronged approach tailored to the specific conditions and potential risks at each site, like a customized treatment plan for the dam.
That's a great way to put it. And it's not a one-time fix. Tailings dams are dynamic structures, constantly evolving as more tailings are added. Monitoring is crucial. We need to continuously track the dam's behavior, watch for changes in poor water pressure, and be ready to adjust our management strategies as needed.
So it's like being a doctor for the dam, constantly monitoring its vital signs and making adjustments to keep it healthy.
Exactly. And just like in medicine, prevention is always the best medicine. By understanding the principles of CSSM, using the right tools, and making informed engineering decisions, we can dramatically reduce the risk of those catastrophic tailings dam failures that have had such devastating consequences.
It's a powerful message of hope and responsibility. This deep dive into critical state soil mechanics has been an incredible journey, hasn't it? We've gone from basic principles to complex models, and it's all about understanding this hidden world beneath our feet.
It has been a fascinating journey, and it underscores the importance of continuous learning and innovation in this field. There's always more to discover about the fascinating world of soil, and that knowledge is essential for building a safer and more sustainable future for mining.
I couldn't agree more. It's been a privilege to explore this vital field with you. And to our listeners, thank you for joining us on this deep dive. We hope you've gained a new appreciation for the complexity of soil behavior and the crucial role that critical state soil mechanics plays in ensuring the safety and sustainability of mining operations worldwide.